what is an intermolecular force like in general?
The force between molecules.
Good, so it's the force that exists between two separate molecules, right? It's the friendship force between molecules. So we have three main types, and we'll talk about the fourth one as well. Intermolecular forces. So let's start with London. So what is the London dispersion force?
Weak.
Good, so it's the weakest of the three. What else do we know about it?
All covalent have it.
Good, everything that's covalent experiences this. What else? What causes this force to happen?
Isn't it like, where like the electrons, like it's kind of like shifting sides, so it's like partially polar at one point, and so that's when they come to interact.
Good, so it's a moment of polarity. Yeah, so it's the whole idea of how everything has electrons. So the electrons in any molecule are moving, and if those electrons momentarily are all on one side, you'll get a moment where it's polar, meaning positive and negative, because those electrons all shift one way, which then can cause it to feel an attractive force between, right? Another way I always think about IMFs is IMFs are like little magnets. It turns the molecules into magnets, right? Where they're attracted or not attracted to each other. So it's caused by those, like, that shift of electrons, right? Electrons moving. What can cause something to have stronger London than something else?
Polarity.
Good, so polarizability is the fancy word. The higher the polarizability of a molecule, the greater its London dispersion force.
How do you-
Polarizability,
yeah.
heads up.
I was gonna ask, how do you know
Like determine.
the polarity of something, or
The polarizability. So polarizability just describes that ability of the electrons to shift, hence like it becoming polar. So it's directly linked to the molar mass of a molecule, or pretty much how many electrons it has. Because the more electrons something has, the greater shift that experiences, and so the greater polarizability. So pretty much the heavier something is, the stronger its London forces will be. Does that make sense? One example I always think of is like the halogen family, because the halogen family are all diatomic, right? So like F2, Cl2, Br2, and I2. So none of them are truly polar, right? Because they're just bonded with themselves. But iodine is a solid at room temperature because of its high polarizability.
That's like my.
While fluorine is actually a gas at room temperature because it's so weak. And then bromine is a liquid, because it's like a little bit stronger than these ones, but not as strong as iodine.
So theoretically, you use bromine to like clean a swimming pool, or fluorine, or like put it in a swimming pool. Or
Oh, because of like similar properties?
Yes.
I would assume yes. I've never really thought about why they use chlorine in particular. And it's not like they're using pure chlorine either, it's like a chlorine compound.
Yeah.
But like, could you use a bromine compound or fluorine? Probably. I don't know, I have to look into that.
All right.
That's a good question. Okay, any other questions or thoughts? That's kind of everything I can think of with London. Okay, our next type of force is the dipole-dipole force. So what do we know about this one?
Stronger.
Stronger than that one, right? What were you gonna say, Taylor?
Well, it depends on electronegativity.
Good, so it's directly linked to electronegativity. Right, this is a permanent shift. That's not how you spell permanent.
Perm A. It's
Permanent.
Nent.
A. A-N-E-N-T.
Yeah, A-N.
Oh, why can't I spell
Just
permanent?
N-T.
N-T.
Thank you.
We got you.
Goodness. Okay, a permanent shift of electrons. So this is a momentary shift. This is permanently shifted because of electronegativity, right? The electronegativity of the atoms is so different that pulls the electrons and they are always dwelling on that side versus the other. How do I determine if a molecule is polar?
So, I mean, you know that electronegativity as a general trend
Good.
is top right, like, is the strongest, bottom left is the weakest. And so if one is more electronegative than another, then yes. Okay.
So that determines if the bond itself is polar. What do I also have to look at for a molecule though?
The difference in electronegativity.
How so?
So like if a fluorine is bonded, or not bonded, but attracted to like something that's less
Oh, okay,
polar,
okay.
then it'd be like, yeah. Like,
So if I have this structure right, we know that fluorine is gonna pull the electrons because it's higher, right? And so the electrons will go this way, but
Yeah, the last thing is like, if like one of them's, yeah, that's what it is.
that's
so
not-
this is my structure. Is the molecule polar?
No.
Why not?
They're like
Because
all
it's just
polar
negatives
exact
with
same way.
negatives.
Yeah, so there is a polar bond, right? But this is the case where the polar bonds cancel each other out, right? So you have a canceling of magnitude, or canceling of the dipoles is kind of way you can describe it. So a big thing with polarity is you look at like the symmetry of the molecule. If the molecule is symmetrical in the dipoles, then it will be nonpolar overall. If it's not symmetrical, then it's not. And that's one thing, just a reminder too, with that idea of making sure you think of 3D structures, not a 2D Lewis shape. Like, because for example, with water, we often draw it like this, which some people would then say like, oh, the dipoles are going to cancel each other out. What's wrong with that logic?
And
Yeah, so remembering what lone pairs do to the shape of it. That's kind of it for dipole. Any other questions about dipole in your mind? I think we've got this down, but just to make sure, can London be
Yeah.
stronger than
That's
dipole?
how it is.
Yes.
Yeah.
Like the stupid bromine question that there was.
Yeah.
They love to do that.
Oh, dude, freaking bromine, man. Messes you up.
The other ones are gas.
Students that are attending the Test Out Utah birthday party, please meet out at the front of the school right at this moment. Thank you.
Utah birthday party?
Can I go to the Utah birthday party?
Where were we invited to the birthday party?
I didn't know it existed.
We're just not as popular as the other people.
That's okay. We'll have our own birthday party.
Yeah.
I'll add cake to our list of things.
My birthday was yesterday.
Was it?
Yeah.
Happy birthday. We should have had a birthday
We should have a
party.
birthday party.
My birthday was in December.
We should have a birthday party for you too.
Maybe we'll have an everybody birthday party after the test.
That's a good idea.
All blow up hydrogen balloons.
Ooh.
Okay, hydrogen bonding. Oh, let me just repeat that. So this can be stronger than that if you're given data. I wouldn't ever make that assumption. So they don't give you like the boiling points and things like this is normally stronger. But if they give you data, and then that's the case where the polarizability of something can outweigh the dipole forces of something else. So, okay, hydrogen bonding, what do we know about it?
Strongest.
It's really strong. It's
Yep.
pretty mega.
It's the best.
I saw HP on
Only happens
Hydrogen
hydrogen is
bond
bonded to NOx.
Good, so you need N, O, or F sandwiched to cause a hydrogen bond to form. Making sure you have it on both sides of the hydrogen ring.
Which if you just had F and H, would it not be a hydrogen bond?
What do you mean, like,
Yeah.
no, because the hydrogen bond is an intermolecular force, so it's the interaction of this with,
Well, yeah.
oh, is that what you're saying?
So that could still be a hydrogen bond?
This is a hydrogen bond.
Okay, okay, you
Yeah.
said sandwich, and that kind of made me think like, it needed like something on both sides. So like
So-
the fluorine would need to be bonded to something else or something like that. I didn't understand your sandwich. but
Oh, my
I get it.
sandwich, yeah. So, because the problem is I've seen like where on an AP test one time it had like this, but then this was like a CL.
No.
It's like that's not a hydrogen bond because both sides have to be N, O, or F. It could be something different, it could be O, right, 'cause it could be like
Yeah.
water.
Mm-hmm.
Does
Okay.
that have to be attached to a hydrogen bomb?
Nope,
Or a hydrogen?
no, so the H just has to be the middle of the sandwich, and then not has to be the outside, but what's after that doesn't matter. Good question though. What else do we know? Why is it the strongest?
Very polar.
Good, yeah, so it's an extreme polar.
Basically dipole, but more.
Yeah, so really I relate everything back to here, and then this is just a momentary polarity. This is an extreme polarity because of two reasons.
Hydrogen is so non, or
Oh,
so
because like the
positive,
electron basically.
Why is
goes-
it so positive?
because just a single proton.
Yeah, because when you
Yeah,
pull
which is
electrons away, right, it's just a proton left. And then NO and F
Are just so negative.
So
have really high electronegativity, so they're really good at pulling it away, so. That's kind of it for hydrogen bonding that I can think of. Any other questions on hydrogen bonding? Let's talk about properties that are related to IMFs. So boiling point.
Higher, stronger ion.
Yeah, so boiling point has a direct relationship, so the higher the boiling point tells you, the stronger the IMFs are, or vice versa. Surface tension, what's that relationship?
It hurts.
Yeah, same.
The higher the surface tension, the higher the IMF.
Belly flop.
Vapor pressure,
Kind of low.
Yeah, it's low.
so if you have a high vapor pressure, what does that mean about IMFs?
Very low.
Why?
Because it's easier to.
Because if they were being held together better, then they wouldn't be vapor.
Very good, very good.
And you back with the hands, you know?
See that, everybody?
Yeah, you see that one, Ryan?
I think that's the main properties that deal with IMFs. 'Cause normally I feel like it's boiling point and vapor pressure are their two favorites.
So
They-
what does it mean by like, so there's ones that I got it wrong. And we're talking about boiling points and IMS. And there's talking about like, the answer key said something about like electron cloud and how the electron cloud was stronger, like which,
That's the definition of polarizability.
is that, okay. Alright.
Yeah, so you can, in place of saying electron cloud, you could talk about its polarizability.
Alright, okay.
But yeah, so, because the polarizability, I once read in one of my college textbooks, I should find which one it is over there, because all of them are in that corner. But they like define polarizability by calling it the squashiness of the electron cloud.
Genius.
What?
Can you say
In your
that?
textbook?
Yeah,
That's really funny.
yeah.
I can totally see it though.
It was a pretty textbook. They had like, it was really, and then every once in a while they had like these random things.
CO2 is
Yeah.
more squashable.
They're the guys who named it
Than
Seesaw.
F2.
Yes, like one of those modes, right? But that's the whole idea is if the electron cloud can swoosh one way, then that side's gonna be more negative than the other. So, does that make sense?
Yeah.
Yeah, good question. Just wording
Students that
choices.
ride the Aquaman bus, you will need to ride the windmill bus on the way home today. The Aquaman bus will not be coming home.
Really good.
Aquaman bus
Bro,
rides the
freaking
windmill bus.
Aquaman
Thank
is
you.
dipping on him.
And students and teachers,
Yeah.
actually just teachers and staff, please come down and have a snack today. It's
You said students, I going down to grab a snack.
Outrage.
They're like, hey, students.
They're like students,
Just
no, you don't get snacks.
I think, yeah, Man. I wanted a snack so bad.
Have jelly beans.
I
They
can
just
just
wait
act
till
like
the
I'm
seventh,
really
dude.
hungry.
They're gonna be
I didn't have lunch today. So.
Yeah.
Can I get 6 of everything?
Yeah.
7.
What was the other thing I was gonna say? Anything else? Oh,
Take all
this is
of
what I
them
was gonna
in
say.
your hands.
So there is another type of intermolecular force that we said I don't think
Oh,
of.
it's the weird covalent bond one.
Ionic.
What is?
Oh, like the
We
one.
do have those two that we'll get to in a second. So we have what's known as
The diamond one, the one that's.
Network
Network
covalent.
covalent, yeah, that's what I was trying to say.
yeah. So two other things. So we have the
I forget
covalent
those
network.
Oh, yeah.
It pops up every once in a while. I don't know. No, on the 3 multiple choice you've taken, is
graphite
there
one,
any
like
question
that,
about
like
network?
diamond.
I always did. No, there was
I
one.
gave up.
There was one.
I mean, it didn't really ask about it, but it was
Yeah, it
on
just-
there.
I forget that those exist, you know?
So what is a covalent network? Do you
It's
guys
like-
remember?
It's like,
They're just insane. Carbon is just.
yeah, carbon.
Yeah, so like
Does it have to be carbon? Like, are there any other molecules? that
silicon can do
it?
it too. So it's the things that can do 4 bonds on one molecule.
So could you get like
Okay.
lead? Or I guess
Lead
that's just
is a
metallic.
metal, so it's a metallic one. So it's really just like those two, to be
So what about
honest.
germanium?
So you put silicon diamond.
I don't know. Germanium probably could, I would assume.
What?
So
The GE.
the biggest thing is
Are
recognizing
those
is like
jelly beans?
IMFs, right, are like between, so like this to something else. A network is literally, they're truly bonded to each other. Right, so it's not like 2 separate molecules interacting. Right, but it's literally like a diamond, it's like carbon to carbon to carbon to carbon and 3D space in all directions.
Oh, I can see how that would work.
Isn't graphite?
That
just
makes so
like-
much sense now that like I'm in the future.
Hang on. I can't.
Say that
hear.
again.
Graphite was like layers.
Yeah, so
of
same
things.
thing, graphite's the same way, it's just flatter, but it's still a massive network of carbons hooked to carbons.
I
So
can
that's
see
why,
how
like,
that works.
A graphite to a graphite layer is intermolecular, it's just blended forces. But graphite within itself is a network. So that's why actually like a single sheet of graphite is crazy strong.
Yeah, graphene.
Yes, but they come apart easy when you write with your pencil, cause it's just blended forces, so. Questions on that?
So how come like you can just, you know, because when you're writing, you're just putting like single sheets of graphite on the paper, or multiple single sheets. So how come it's so easy to rip apart?
Well,
Cause what are you ripping apart?
You just
Paper.
pull it apart.
But the graphite's on the paper.
But they're in little sheets.
Well, that's just like if a diamond is on a
You're
table,
ripping
you
in
just
between.
wipe it off.
So yeah, you're not actually ripping, like at the molecular level, you're not breaking the actual graphene apart.
So is the graphene like, come on buddy, even though you're on the other half.
Yep,
you're coming
because
over.
it's not-
Circum Rec, please call the front office at 785-756.
Good thought though.
wait,
Circum Rec, thank you.
how do erasers work?
Tell me.
I don't know.
Friction.
Wait, what did you say? Razors?
Whoa, dude,
Erasers.
the pink ones are way better than all of the other ones.
Oh yeah, what about these ones?
Is it?
The
And
gray
that's not what I was talking
Gray
about.
ones are cheaper than
I don't think
So
Gray
our
ones are
pencil, right, when we
amazing.
write, the
No,
graphene
these
layers
ones,
are
these
just
ones.
slowed down.
Yeah.
And so it just creates friction to pull them back up, and they just end
So
up
what
on
is
my
an eraser then?
I also like
It's just a super.
It's just something
like
that
sandpaper.
creates friction, I guess.
Yeah, but what is it?
It's like rubber.
Is it like super chill sandpaper?
It's definitely not sandpaper. 'Cause
super chill sandpaper.
Well, no, it's like sandpaper,
Super
but
chill.
it's not
Oh,
inert,
yeah.
you know, it doesn't hurt.
I like that description.
Amenable eraser. Sick, bro.
What?
We
Amenable
do also
eraser.
have something known as the ion to dipole force. We
Oh.
often don't, you've seen questions about this one a lot, we often don't refer to it by name. But this is the force that exists when you have a pure ion, so something positive, interacting with something else that is polar, so like water.
Lindsay Erkenbrack, please ring into the main office. Lindsay Erkenbrack, ring into the main office.
So this link that we talk about, that is defined as an ion dipole by name. Once again, by name, you don't really notice much as what it
But
does.
specifically just a polar thing, but it's like super insane polar.
Well, it's just saying you have an ion that's connected to something that's polar.
Yeah, it's basically just like racing.
Oh yes, it's very similar to that. Few things that do seem to come up a lot is what 2 factors help increase the strength of an ion dipole?
The so if it's like Na, if it was like Mg,
There you go. Why?
because Mg is 2 plus,
Yeah.
Coulomb's law.
So
Oh.
Did
magnitude,
you hear that? I just used to span.
And
Wait.
direction.
Sporbs.
not
Dang
why.
it. I have too much things. in
It
my
does start
brain.
with a D though.
Died.
Direction and magnitude.
Oh, yeah.
Direction.
That's what you said before. You
Like-
can't repeat the same word with excitement.
Direction.
Yeah. What is
There it is, Kylie.
That
What was
thing
it?
in front of you.
It's my.
Direction.
Your what?
Distance.
My heart.
Which,
Oh, I didn't realize, I thought like it was 2D words, I'm like, well, we already went.
Wait, okay, what is Coulomb's law again?
Basically, if like the magnet, yeah, it's magnitude and distance, that's what it is. If the magnet is like more magnitudable, like NA plus.
What?
Say that again.
That's not quite how this works.
Mag, I know, isn't it kind of weird?
Coulomb's law, Gavin, is, in simple terms, it's the law that explains the force of attraction between anything that's positive and anything that's negative. So this law applies outside of atoms. The atoms have positive and negative, so it applies to them as well. Where when you have a positive and a negative theme, what affects that force of attraction is the magnitude of the charges, so how positive or how negative they are, and the distance in which they're related. The closer things get, the stronger the force. Now in terms of atoms, that's mostly about the size of it. Is the bigger something is, the lower the distance is. I mean, the farther distance is, back up. Let me repeat that sentence again. So the farther away, or the smaller, which one's smaller, NA or MG?
NA is. No,
MG
MG
is smaller.
is.
Good, so
It
MG
always like
actually does
flips me
wrong.
around that like, even though it has more stuff, it's still smaller. You know?
It's cause
I
it's
can't
like
go that small, I might
epic.
MG too big, but you know what I'm saying? So the smaller something is, the closer the distance, and so the stronger the force would be.
So it's like a double mega super duper Coulomb's law, where it's like distance
So,
and
is it-
magnitude.
I kind of like think of like the smaller the distance. I'm kind of thinking of like a hug. Like
A hug?
the closer the
H-U-G?
two people are together, like the stronger the hug or something.
Yeah.
Yeah,
Oh,
because
yeah.
you know your average hug just.
And if the one person's way more strong, you just totally jacked, man, he's gonna break your back.
Yep.
Like Bane.
And then
Just think
So
of Bane and
Coulomb's law is the hugging law.
think of Bane and Batman as just like
I
hugging.
mean, I'll remember it
But Bane's like
now.
a really good hugger.
Because of the hugging law.
They're gonna be like, what is this kid doing?
It's like all scientific and then you.
No, it can't be hugging because all the other ones are like weird names. It has to be like German or something.
Well, no, it already has a fancy name.
What's,
But
We're giving
What's
it a
hugging in
nickname.
German?
yeah, what's hugging in German?
yeah.
Does anybody?
It's Coulomb.
No, hugging in Italian is hugino.
It's Fußgänger.
Hugging in Canadian is hugging, eh?
According to the Fußgänger law,
While we're talking
What's
about,
the Fußgänger law?
he said that's what.
No, that's not. Fußgänger zone is like the pedestrian zone.
That's even better. Let's call it the Fußgänger.
Pedestrian zone law.
No, it's actually super sick because it's like just a place in the middle of a city where there's no cars. So it's like this weird like city feel, except it's like the sizes of roads, except it's all paved, and it's like I don't
Dude,
know,
them Fußgängers,
It's kinda
man.
sick.
You watch out for them.
a Fußgänger zone.
You're gonna get
So kind of
Fußgänger.
like Central Park.
Okay, wait, where's the
No,
band
it's like
field?
the band
Is
Is that the one over there?
It's
by
just
the
like
tennis
a-
By the tennis courts? Okay, yeah, gotta make sure.
Okay, let's review metallic bonds at the molecular level, what goes on inside a metallic bond.
It's like
Lots
sea
of
of
electrons.
electrons.
See, what,
Dude, I feel like
because of the electron C, what are common properties of metals?
It's malleable.
Yeah, malleable, good conductor.
Mamo.
I have no idea, bro.
Why are they good conductors?
Because like it's just like
Just
the electron just kind of shifts.
Conductors need movement, right, and the C gives it tons of movement.
Otter moon.
So you don't know.
Ottoman law.
Otter moon.
According to the law, right?
Dude, everyone just needs to have that on them.
That's not.
Alright.
Like take their phone to the AP test.
Alright, this is hugging.
Is that allowed?
Yes.
What?
Sound like
What are
scary
the two
onions.
main properties? I mean, they're always shiny.
Shining.
And that kind of deals with the movement of the electrons.
I actually helped my brother with his homework in college. He's like, I need your help. I'm like, all right.
Oh, let's review this. This
Your
topic
brother,
is
Yeah, your brother was at the math.
He was at the math club thing when we were
Oh,
taking
yeah.
a
What is
test.
shiny
Yeah.
but in different words because there's a better word.
Uh,
Weird.
let's
Knows
do-
math.
lustrous.
There was a lot of
It's
good in that.
Spain.
Yeah.
There's
He was talking about stuff
Yes,
with one of the other kids in my class, and I
but
was just like,
pronounce the
how do you even know?
I know, right? Yeah.
Okay, stay with me, cause I got 3 minutes and then I gotta go.
Alright.
So with metals, what is an alloy?
It's a combination of two.
Good, so it's when you melt two metals together, right, like brass and
It's
bronze.
alloys, like substitutional and institutional.
Good, so you have substitutional alloys. I don't have this popped up on any of your practice tests yet?
Yes.
It's kind
There
of one of
was,
those things that
no, there was
everyone's
one that was like, which one's strong, like, why would this be stronger or something?
That's normally the.
Or it was, why does the
Oh, yeah,
carbon,
it was
why does the
always-
carbon make the iron more brittle?
Yeah.
I put
No,
it-
you just made it stronger.
I guess I got it right.
No, it made it
I
stronger,
got it
right? The
wrong.
carbon made it stronger.
So it said why,
No,
the
wait,
carbon made
yes.
it more brittle.
It did?
No,
Yeah,
it
so
made
it
it
was stronger,
stronger.
more brittle, and with less carbon it was more like bendable.
Oh, I
Oh,
We didn't go
more
over
carbon
the
makes it
answer.
into
was-
like an ionic.
Where's the
Oh.
packet? The correction packet.
From today.
No, that wasn't for today, that was for last time. That was
I took it today.
FRQ.
That was for today, bro.
That was for today?
That was the multiple
Where was
choice
the-
that we
where's the
corrected in class today.
I don't
Oh.
know.
Who knew?
That's a shame.
We'll pull it out though. Sorry, I wanna get through this thought before we end.
Yeah. I got it.
So what is a substitutional and an interstitial alloy? Do you know the difference?
A substitutional like
Good, so one's about big ones, one's about little ones.
substitutional like replaces them, and interstitial just like squeezes in between.
Yeah, so it's like you have your metal, right? So these are all one, and substitutional is you substitute it with something that is similar in size, but maybe a different property.
Mhm.
So like maybe it's more conductive than that metal or less conductive.
So like would brass be substitutional or institutional?
Brass is copper and zinc.
Yes. I literally,
There's
I would say
similar
that's
in size.
substitutional because
That's
they're
probably
pretty much the
substitutional.
same size, right?
Yeah.
yeah.
But then interstitial, yeah, is the one where you substitute in something smaller.
But like carbon isn't like iron, but it like does it still work in interstitial?
It's
Car-
definitely
not
interstitial.
iron. Carbon isn't metallic, but it still works.
Yeah, so you can do things that aren't metals to once again bring in certain properties
Okay, got it.
like that you might be going for. So
Dude,
yeah,
I'm
so
sure
it kind of
it's
just depends. Like interstitial will often become more brittle,
He's saying it
or
was
like
less
they'll,
malleable.
it's stronger,
It was
but it doesn't
stronger.
bend, right?
But brittle in the sense
These
that
ones
it would
often
break
are
rather
brought
than,
in for like
uh,
conductivity properties, I'd
like
say.
Yeah, probably.
So,
Wow.
It was stronger.
Alright.
That's what
So
I
he
thought.
just has a weird
Good
brain.
review.
Any
High
last
five
questions?
everyone with the
Good
air, 'cause
review.
COVID. High five to you.
Another.
There you go. You got a high five. I gotta go. See you guys. Party
Good
hard.
luck
Good
to
job.
you, Paul.
Oh yeah, dude, we're gonna win. If I win, I mean lose.
Yeah, you are.
that makes sense.
What, Gavin, are you leaving?